Yeah, so welcome to the Temporal Graph reading group today, everyone. We are very glad to host Andrea Cini, and I will get to the speaker introduction here. So Andrea Cini is a postdoc researcher at the Graph ML group and IDSIA um, at USI. He obtained his PhD from USI under the supervision of Prof. Cesar Alipe with a thesis on graph deep learning methods for time series forecasting. And previously, he was a visiting researcher at Imperial College London and earned his master and bachelor's at the Politecnico di Milano. His research focused on relational time series processing. In particular, he introduced the methods for forecasting data reconstruction and probabilistic graph learning. So his work has been published in top ML venues, and he also served as reviewers. He is also a creator of the Torch Spatial Temporal Library. And yeah, I will hand the mic to you.
Thank you, Andy, for introduction, and thank you for hosting me at the reading group. And yeah, let's start with a bit of introduction on what we will talk about today. The modern approach that people use in deep learning for time series forecasting is that of training a single neural network, usually a single large model, on a collection of related time series. In this way of processing the data, each time series is processed independently from the others while keeping the parameters of the model shared. This basically makes the procedure very simple, efficient, and also allows for training these large models. The downside of this is that the dependencies that might exist among these time series are discarded. One way around this is to use graph deep learning, as you know, if you have been following the previous meetings of this reading group. And if you use graph deep learning, the dependencies can be directly embedded into the processing, and the resulting models can operate on sets and subsets of correlated time series while still keeping the parameters of the model shared. However, this is like easier said than done, and there are inherent challenges in applying this kind of processing and framework to data coming from the real world. So in this talk, I will be talking about the framework for time series forecasting based on graph representations that we developed together with colleagues here in Lugano. And in particular, I will talk about how to address the main challenges in applying this framework. The first one is that of dealing with the many different local dynamics that might be present in a collection of time series. The problem of dealing with the missing observations, missing data, so irregularly sampled time series. The problem of learning a dependency structure from the data when we don't have one to start with. And also, finally, I will also talk about some methods to address the computational scalability of the method. I'll start from an introduction of the problem settings, also setting up the assumptions and what we need to define this forecasting framework. And by the way, if you have questions, really feel free to stop me. Let's keep this interactive and friendly. So we assume that we have available this collection of n correlated time series. Each one of these time series can be multivariate, so we can have a vector of observations associated to each time series at each time step, and we can also have additional covariates associated to the target time series that can be both dynamic and static. And in the case of static covariates, we talk about attributes. While we use the small letters to denote the observations at the single time series, we will use the capital letters to indicate the stacked representations across the time series collection, and we call this dimension, so the dimension that spans the collection, the spatial dimension. We assume that the time series are generated by a time invariant stochastic process, and we assume the existence of a causality, a Granger causality among the time series, which means basically that we assume that the forecast for a time series can be made more accurate by considering the other time series in the collection. Furthermore, we assume that the observations across the time series are homogeneous, and that these happen synchronously over time and also regularly. We don't assume instead that every time series is generated by the same process. And it's also important to stress that while these assumptions might sound very restrictive, in practice they can be met with the appropriate preprocessing and also can be relaxed, as we will see later on. For what consists the problem, again, we are trying to do time series forecasting. So given a window of past observation for our time series collection, we want to forecast the next age observations in the future. And we want to do that by learning a parametric model of our data. In particular, we will focus on point forecasts, so on forecasting values, but probabilistic predictors can be also considered. So the first important distinction, which I think is very crucial when talking about like deep learning for time series forecasting, is that between local and global models. So for local models, these are trained on a specific time series. So we will have a different set of parameters for each time series that we want to forecast. And this is, I'd say, the standard statistical approach to time series forecasting, like with the ARIMA methods, you will have a single model that is trained on a specific time series. While in the deep learning approach, as I was anticipating at the beginning, we usually use what are called like global models. So we have a single model that is trained on a collection of many time series that are related somehow, so that they share some similarity. So the advantage of the local approach is that the resulting models will be tailored to the specific time series we are trying to forecast, but this can result in an efficiency, both like from a computational perspective, but also from the perspective of like sample complexity. In fact, global models have like an improved sample complexity that comes from training the model of samples coming from many different sources, which allows for training more complex models. The drawback of the standard implementations of both of these approaches is that they neglect these dependencies that might exist. The standard option, the naive option to deal with the problem would be to train a single model, a local model on the input time series as if they were like a single, very large multivariate time series. Clearly, this suffers from the curse of dimensionality and might result in like poor sample complexity and also poor scalability. Alternative, it can be possible to use models that operate on sets of time series, so like deep sets models. And these are global. So with a single set of shared parameters, we can forecast any subset of time series. And for instance, this can be implemented by using attention-based models, where here the attention would be computed with respect to the spatial dimension. The downside is that this would not exploit eventual prior that we might have on the structure of the data, which might result in high computational and sample complexity. There are also other methods that exist and that are possible to use. For instance, one might use some kind of dimensionality reduction to extract some shared latent factors and use these latent factors to condition the forecasting model on the entire collection, but this clearly would lose the local fine-grained information and would still suffer from scalability issues. Now we can start talking about our graph-based methods, and Yeah, I mean, all of you are familiar with the idea. So the idea is to exploit a graph-based representation to encode these dependencies that might exist among the time series and use these dependencies as an inductive bias to improve our forecast. So these dependencies will be encoded in a graph adjacency matrix, which can be asymmetric and dynamic, also depending on the problem. The associated with each entry of the adjacency matrix, we might have also edge attributes, which can be both categorical and numerical, again, depending on the target application. This is a sort of summary of the inputs that we have available for our forecasting architecture at this point. So we have our target variable together with exogenous variables that can be both dynamic and static, plus this additional relational information. Relational information that we want to use to condition our forecasting model, and this will act as a sort of regularization to basically localize the prediction with respect to each node, each input node, each target time series. The idea is that this structure can help us prune eventual like spurious correlations that might exist in the time series collection, thus making the model more scalable with respect to the standard multivariate approach we were talking about before, while at the same time keeping the parameters of the model shared, so keeping the model global. We usually call these kind of architectures that are used to carry out this forecasting spatiotemporal graph neural networks, and we will focus on those based on message passing. In particular, we consider this template architecture where we have an encoding layer, which is basically used to do a first encoding of observations across the time series collection at each time step, followed by a stack of spatiotemporal message passing layers, which are the layers where the propagation through time and space happens in the network. The representation extracted by this layer can then be mapped to prediction by using a decoder layer, which is basically a readout. For what concerns the spatiotemporal message passing blocks, this can be seen as a sort of extensions of standard message passing operators, so sequences. So here we have a sequence of observation associated to each node. So the different blocks that compose a message passing operator, we will have to be designed, redesigned in order to handle these sequences. Luckily, from the literature, we can choose from many possible different sequence modeling architectures, again, depending on the application and the problem that we want to target. Now we can start to talk about the challenges, and we can start from the problem of dealing with local dynamics, and in particular, about this paper that was already discussed in a previous think meeting of the reading group. Now I'll try to give you talk again about this within this framework. So as anticipated, given the previous taxonomy of forecasting model, spatiotemporal graph neural networks are global models. And this is good news since they can handle arbitrary node sets and they can exploit this relational structure to condition the forecast at each node, at each time series with respect to the neighborhood of that node. However, they might still struggle in accounting for all the many possible heterogeneous dynamics that might be present in the collection of time series that we want to forecast. And this might result in models like needing very long observation windows or a very high model capacity. So a possible way of going around this is to use hybrid architectures. So basically architectures that somehow include some global component. One straightforward way of implementing this is to take the template that I presented before and make some of the blocks of the architecture local. The idea is that for for instance, for the encoder and the decoder block here, we could learn parameters that are specific to the time series that we want to forecast. Clearly, the resulting model would be able to capture this heterogeneity, these different dynamics much more easily, but with the downside of requiring a larger number of local parameters depending on how these encoding and decoding blocks are implemented. Now, one way of amortizing this cost is to consider a table of node embeddings rather than an entire layer or stack of layers. Here, the idea is that we would have a table of learnable parameters where each row of the table is basically a vector of learnable parameters associated to a node. And we can feed these embeddings to the encoder and decoder to basically make the processing more local, so more specific to the single time series that we want to forecast. The advantage here is that this allows for keeping most of the model's parameters shared, so to keep all the sample efficiency advantages that we were talking about before, while localizing the processing. The downside is that, nonetheless, the number of parameters would scale linearly with the number of time series. But if we have some constraint, we can use intermediate solutions where, for instance, we could learn embeddings for clusters of time series rather than for each signal that we want to forecast. The other downside is in the fact that using hybrid architecture, you would lose the possibility of using the model inductively. And while this might sound like a limitation, it can actually be an opportunity, for instance, in a transfer learning setting. So in the settings where we have a small amount of data that we can use for fine-tuning our model. And the idea is that in these settings, we can keep the bulk, the core of the architecture shared, global, and just fine-tune these local components. In particular, this can be done, as we showed in the paper, very efficiently for the node embeddings, like by imposing also some regularization on the latent space of the embeddings. And if we look at the empirical results, here are, okay, at the top of the table, we have results for the reference architectures that were some reference architecture that were developed by following the template architecture I showed before. And at the bottom, we have some architectures from the state of the art, and these are performance across 4 popular benchmarks used in the field. And we see that by adding these local components, these local embeddings, the performance improves by a wide margin across the board. And if you look at a transfer learning scenario, here what we did was basically considering 4 different traffic networks, training a model on 3 of these networks, and then fine-tuning and testing on the left one, on the left out one. So the first observation here is that the model that performs zero-shot forecasting, so the global model that is not fine-tuned, performs the performance of this model are definitely worse than those that perform some kind of fine-tuning here on just a week of observations. And the second observation is that the hybrid architectures, in particular those using embeddings, perform much better than the fine-tuned global model. In particular here, this variational and clustering are 2 types of regularizations that we studied in the paper. And this shows that if you regularize this embedding space, you can get even better performance. If we can then talk about the second challenge, which deals with the problem of missing data that we addressed in several papers in the last few years. And the idea is that, well, if you are dealing with data that come from the real world, so from real world applications, you will always have incomplete time series and missing data. And this is bad news because most of the time series analysis tools that we have available assume to operate on complete sequences. This motivates the need of having methods to reconstruct this missing observation. And what we tried to do across these different papers is to exploit this graph-based time series processing framework to carry out this reconstruction. So the first model we proposed a few years ago is called GREEN, which stands for Graph Recurrent Imputation Network, which basically is a bidirectional recurrent neural network where the gates of the recurrent cell are implemented by graph neural networks. It's bidirectional, so it can take into account dependencies that are both backward and forward in time with respect to the target time step for the reconstruction. And clearly it can also, thanks to message passing, take into account dependencies across the spatial dimension. Together with this bidirectional processing, we also have a final message passing step to take into account the concurrent observations at the neighbors of the target for the reconstruction. And as I will show, this approach can work very well in practice and it works very well in many settings. And we had a lot of success applying this to different applications. However, being an autoregressive model, it can suffer from an accumulation of error anytime we are trying to reconstruct observations over a long sequence of missing data. And the alternative that we considered is this operator that we introduced that we call cross-attention, spatiotemporal cross-attention, where the idea is that you are computing attention scores between neighboring time series. And intuitively, attention prevents this error accumulation that can happen in autoregressive models. And you can, of course, build architectures by stacking many of these layers, with the downside of this being computationally expensive. As you know, attention is has quadratic complexity. But we showed that you can reduce this computational complexity by introducing some hubs and computing attention with respect to these hubs rather than with respect to each single time step. And if you look at the performance, here it's again across several data set and several missing data distribution. We see that the graph-based approach that we introduced, in particular, this one with an H is the hierarchical version of attention, so the one that is more computationally efficient, perform much better than both RNNs and also other attention-based architectures that do not include this graph component. So if in these settings, so the standard settings, we consider that the performance of spin and green are somehow close. If we perform a sensitivity analysis with respect to the rate of missing data, we see that the attention-based model is much more robust to an increased number of missing observations. We can then talk about latent graph learning. So here the problem is that as you might know, as you might have noticed, this relational prior information is not always available, but we would still want to use this kind of relational processing when processing our time series. And we can do that if we learn the graph directly from data. In particular, we focused on a probabilistic approach to the problem, where the idea is that instead of learning the graph directly, we learn a distribution over graphs so that the graphs sampled from this distribution minimize your forecasting loss, your forecasting error. These graphs can also be made dynamic by basically conditioning the distribution on a window of observation. And the nice thing in this probabilistic perspective is that by acting upon the parameterization of the graph distribution, one can embed different sparsity priors on the graphs being sampled. The challenge here is that computing a gradient with respect to this sampling procedure is challenging and usually computationally expensive. In particular, you might want to use the standard pathwise methods tricks. But the problem here is that while these methods are easy to implement, for when you are using a discrete probability distribution, these usually rely on some kind of continuous relaxation that would make any subsequent message passing operation scale with the number of nodes squared. The framework that we consider instead is based on score function gradient estimators that are basically based on this rewriting of the loss, where the gradients is computed with respect to the score function. So with respect to the this log probability here. And this is something that we want because with this setting here, we can keep the computation sparse when computing the loss. So we can have both sparse for the forward and backward passes that are sparse. And clearly, both of these expectations here can have Monte Carlo estimators, so can basically be estimated by sampling the distribution. So what we did was introducing a framework for a time series forecasting based on these score function estimators that, as I was saying, have these advantages of allowing for sparse computations, but have the drawback of usually having a very high variance. So we introduce a learning architecture and specific parameterizations for the graph distribution. And for these parameterizations, we introduced ad hoc variance reduction techniques to make the method actually usable in practice. In particular, we considered two parameterizations of the graph distribution that both are based on the idea of having a score associated with each edge. The first parameterization is very simple, so it's basically a Bernoulli random variable associated to each edge. So each edge is sampled independently from the others. While the second parameterization is a bit more complex, so we are sampling up to k neighbors for each node by sampling without replacement from a categorical distribution. And this is nice because basically allows to impose a sparsity constraint on the graphs that we are learning. So for these two distributions, we introduced estimators that we also show in the paper. Some theoretical arguments for this have a reduced variance. So the first one is basically, okay, so if we call delta the cost function, so basically the forecasting loss, computed with respect to a specific graph, we show that you can reduce the variance by subtracting to this cost the cost computed with respect to the Frechet mean of the graph distribution, where the Frechet mean is basically a generalization of the concept of mean to objects like graphs that are not embedded in Euclidean geometry. The second method instead is based on a surrogate loss, which basically reweights the different components of the loss that we are trying to minimize. And the idea here is to give a different weight to the error at each node, so that when we are changing the probability of sampling a specific neighborhood for one node, we are giving more weight to the error at that specific node rather than on the full graph. Clearly, this introduces some bias. So we introduced this hyperparameter that basically allows for balancing this bias and variance trade-off. So if you look at the empirical results, here these are results on a synthetic data set where basically the model is fixed. So we are just trying to learn the graph. And if you look at the left side, here we are using the standard objective, so no, not the surrogate loss. And the dashed lines are basically the learning curves when no variance reduction method is used at all. And you see that the sample complexity is very high. So the variance here is very high and you are learning very slowly. And you see that as soon as we use some variance reduction methods that we were talking about, the situation improves by a lot. It basically makes these approaches usable in practice. And this is even better when we also use the surrogate objective. Now we can talk about scalability, and also this is something we also discussed, I think, in a previous reading group. And this was the best paper award at the first temporal graph learning workshop. So some of you might already be familiar with this. But yeah, clearly the two main relevant dimensions when we are processing data and time series within this framework are space and time. So the number of time series we want to process and their length, the number of time steps. Standard spatiotemporal graph neural networks architectures have a time and space complexity that usually scales with the length of the sequence times the number of layers in the architecture times the number of edges in the graph. And you can imagine that this can become quickly unaffordable if you want to apply this framework to forecasting problems in large sensor networks. And clearly, you cannot use a naive subsampling strategies. Otherwise, you would break the spatiotemporal dependencies we are trying to model here. So the idea that we explored is that of preprocessing based methods that have already been used in scalable approaches for doing predictions in static graphs. Basically, the idea is that you want to perform all of the propagation steps, in this case across the graph, ahead of training, so that when you are training the model, you can sample this data, the representations at each node as if they were IID. What we did was extending this preprocessing approach to the spatiotemporal setting by introducing SGP. SGP, which stands for Scalable Graph Predictor, which is basically an encoder-decoder architecture where the decoder is the only trainable component. And all of the propagation through both time and space happens at this encoding step, so that also in this case, so when we are also introducing the temporal dimension, observations can be sampled uniformly through time and space at the training time, thus getting rid of the dependence on sequence length and graph size for what concerns the computational complexity. So to carry out the encoding, we used this approach, which basically consists of two steps. The first one is a deep echo-state network, which is encoding the temporal data along the temporal dimension. And a deep echo-state network is basically a randomized RNN, which is initialized using an ad hoc procedure, like an ad hoc strategy, ahead of training and then kept fixed. So it's basically never trained. But from an high level, it can be seen just as a sort of training-free sequence encoder, a sort of a temporal feature extractor. And then these representations are propagated through the graph by exploiting powers of a graph shift operator, which can be, for instance, normalized graph adjacency matrix. All the intermediate representations throughout this processing can then be concatenated to build a final encoding. A final encoding that can then be mapped to prediction by the decoder that can be implemented, for instance, by a standard MLP that can exploit the rich pool of features extracted by the encoder. Again, this can be trained by sampling this representation as if they were IID, because all of the dependencies have already been accounted for in the encoding step. In the paper, we also show that you can improve efficiency even further by making the first layer of the MLP sparse by exploiting the structure of the embedding. So if you look at the performance in this case, these are two very popular benchmarks in traffic forecasting. We see that SGP can match the performance of the state of the art in these two very popular and used benchmarks, while being much more computationally efficient. So these are data sets that we designed, benchmarks that we designed specifically for the study, that have a very large number of time series and many nodes, many edges. And you see that, again, the performance matches the state of the art, but SGP is much more efficient. So it has a very much higher throughput and also a lower memory consumption. The downside of this is that you might need a considerable amount of disk space to store the intermediate representation. This is particularly true if your time series are very long, and that you might be more reliant on hyperparameter selection, since a part of the architecture is not being trained end-to-end. And yeah, this concludes this overview. And the takeaway is that recent research on these methods, so here the spotlight was on our work, but clearly this is a collective effort, has led to the development of a very mature and effective forecasting framework, exploiting this graph-based representation and graph deep learning architecture. And challenges definitely exist, but the available tools do improve the effectiveness and applicability of these techniques. And there are many possible directions for future works, and also a lot of real-world applications where these methods can really have an impact. We also developed a library to implement and design methods and models based on the framework I've been talking about. And this is open source on GitHub. And yeah, of course, as I've already said, this is the result of amazing teamwork, and in particular with Ivan, Daniele, and Cesare, we wrote a tutorial paper on the topic that you can find on archive. And yeah, thank you for listening to me, and I'm available to answer your questions if you have any.
Yes. So can you hear me?
Yeah, I do.
So thanks for the amazing presentation. I think it's a lot of content and super well presented and very digestible. So that's
Thank
that's
you.
nice. I do have some questions that I post in the chat. So feel free to post more questions in the
Yeah.
chat as well, or just like unmute yourself to speak. So when you were talking about the first paper, so I'm curious, have you think about how would you build a like foundation model just doing zero shot basically, or very limited adaptation to new data sets?
Yeah, I'd say it's an open question. Let me go back. Let me try like this. So, as I was saying here, so theoretically, if you have like a long enough observation window, the model with enough capacity, and of course enough data to train it on, you could be able to get away with an entirely global model. Like in principle, that is possible, right? We have a universal function approximator, and the theory is there.
Right.
The issue is that this does not always work well in practice, right? So there are inherent challenges in doing that, like access to enough data, data that should be diverse enough, but at the same time should allow for learning like some general model. So I think it's still an open question, and there are like many possible ways that you could consider, like for tackling the problem. Like there are people working on continual learning. So you could start from a model, and then as you see more data, you could there are methods that somehow update your model or add some of these components in order to take care, like to account for all of the possible additional dynamics and time series that you end up seeing when actually using the model in practice. Um, yeah, I think it's an open question, really. Of course, training on larger collections and more capable models um, it's like, if you can do that, then yeah. From what we have seen, these hybrid architectures work well in practice if you want something that is targeted to a specific problem.
Right.
At the moment, it's what I would recommend you doing if you are interested in a specific application.
Right. Right. Yeah. So thanks for the detailed answer. I think that makes a lot of sense. Um, and you already show some results here that you can transfer within the same domain, right?
Yeah. Yeah, also in the paper, there are there are a lot of results in this transfer learning setting. And in some of them, we show that even like a few days of data, so a very short observation window is enough to get you started, right? And to get reasonably good predictions.
Mhm.
And like for these kind of applications, it's reasonable that you start making your predictions after you have seen some data. So yeah.
Makes sense. Um, So for my second question is when the I so your work on learning the graph structure, I think that's actually like super interesting. So in some of my collaborations, well, like we were thinking about the same problem. So here I think you're taking a more probabilistic approach, which makes sense. But I haven't like read the paper like or the proof. So does the problem converge to like basically retrieving the true graph as you get enough samples for your Monte Carlo?
So it's okay. So in this setting, the graph that you are learning is the one, let me go here, that minimizes this loss here. So it depends also on the model here, f theta. So if the model, so if the process that is generating the data is identified, so if you know the model that is generating the data that you are observing, then what you are actually trying to do is to learn the graph that, given that model, is the most plausible. So the most plausible with respect to the data that you are observing. But since in most of the cases you don't have that model, you have no guarantee of learning like something with a physical meaning. So like, for instance, this graph does not have a causal meaning in this setting here. There are other colleagues here in Lugano that are doing very interesting works on instead learning a calibrated probability distribution. So if the graph is really like stochastic, are there any methods that we could use to learn a distribution that is not just giving you the graph that is in average producing the most accurate predictions on your training data, but instead you might want to actually somehow estimate the uncertainty on the edges, right?
Mhm.
But getting back to your question, since here the model is learned, so even the forecasting architecture is learned, the graph that you are learning very much depends on the downstream forecasting model. So if you look at here,
Right.
yeah, it's basically the graph that is giving you the best performance within this message passing architecture.
Score based. Yeah. Makes
Yeah.
sense. Um, but I think theoretically, if you know the ground truth graph, like you can, if you have the problem where you know exactly what the graph structure is, you have the observed time series. Theoretically, there might be some way to derive some bound on, say, if you do with this sampling, at the limit, you will converge. This time series runs long enough, it should be able to recover exactly like I'm just don't know if that's something that, that's
I
possible.
think I think the assumption that you would definitely need to make to say something about like the identifiability of the graph is that you should have an identified model. So you should know which is the process generating your data.
Right, right.
If you know that, like assume that the process generating the data is like a graph polynomial filter, which by the way, that is what we were doing here,
Mm.
then you might say something like in this synthetic data, so where we know the process generating the data and we can use that and so on, we were able to retrieve the true graph, right?
Right,
But
right.
in the general case, might be a bit difficult, yeah, without making any assumption on the data generating process.
Mm. That makes sense. Yeah. Yeah. And the graph structure itself is also somewhat stochastic. Like even if you have some bias on it, it could be just one observation
Yeah.
of the graph. Okay. Yeah, makes sense. Yeah, so thanks so much for the talk. Is there any more questions in the chat? Feel free to post now. Um, or we can wrap up the talk for today. Yeah, okay. So thanks everyone for coming to the talk. Um, oh, I think there's a question.
Yes,
Your
I have a question. I'll say it. It'll be faster than typing
Yeah.
it. So we talk. This might be a beginner's question, but we talk a lot about time series prediction in traditional statistical settings when you do like ARIMA type um,
Yeah.
uh, forecasting. You first assume and you test that your time series is stationary. How do we do that with graphs?
So here, within this framework, we were assuming that the time series is all of the time series are stationary, and that there exist these correlations and dependencies, this Granger causality among the time series. So yeah, here we don't at least within this framework, it's an assumption to start with, but also in my lab, and if you look at the tutorial paper, there is also a section dedicated to this. We also developed, Daniele Zambon and Cesare Lippi developed a statistical test to test that the residuals on the prediction residuals um, on these spatiotemporal graphs are basically white noise, so are uncorrelated.
Okay.
So if your model is well specified, that there are tools that can tell you that okay, you are actually doing a good job in forecasting your collection of time series. There are analogous tools that you can use and that are based still on this idea of exploiting this structure. Because, you know, if you are looking at correlations and your data are very large, like these very large collections of time series, you are most likely to find some spurious correlation. But you can exploit this prior knowledge and this structure also to make your statistical tests more powerful.
Okay. Well, I'm definitely going to read your archive paper with a lot of interest. Thank you very much for
Thank you.
the talk.
Thank you.
Yeah. So thanks so much for answering the questions. There's still one more in the chat, but yeah, but like feel free to stay and join the discussion if you want to. So there's one more question in the chat. Why can't we use a neural ODE to model time series?
Yeah, so you can, like, there are also papers that within this framework of graph-based methods use continuous time models. In particular, there is Alessio Gravina and Davide Bacciu that have a few papers on like continuous time models within these kind of settings. Also, Daniele Zambon and Cesare are co-authors in one of these papers. So yeah, definitely you can. What I've been talking about within this talk is discrete time, but there are also continuous time models.
Yes, sounds good. Yeah, so thank you everyone, and let's thank the speaker again. And we'll see you at next week's reading group.
Thank you. Bye.
Thank you.